Hello everyone, I am Kalyani Nimbadkar
And I am Swati Humne
We both are student of MSc first year.
from Department of Physics, RTMNE.
We both are explain the Cauchy integral theorem. So let's start. Firstly, the statement of the theorem, that is, if a function f of z is analytic and its derivative f dash of z continuous at all points inside and on a simple closed curve C, then integration of f of z dz is equals to 0. For more convenience, so I have already written this theorem. In this statement, one line is most important, that is f of z is continuous. So this means that f of z is differentiate at each point.
F of z is analytic function and analytic functions are always satisfied the CR equations. CR means Cauchy-Riemann equations. In this theorem, CR equations are used. That is del u by del x is equals to del v by del y and del u by del y is equals to minus del v by del x.
Let's start the proof of this theorem. Proof. Let the region enclosed by the curve C be R and let f of z is equals to u plus iv and z is equals to x plus iy. Differentiate the z, that is dz is equals to dx plus I dy. Now integration of f of z dz is equals to, put both the value in this equation, is equals to integration of u plus iv, that is f of z, and dx plus I dy, that is dz. After that, separate the real part and imaginary part, that is u dx and v dy. Imaginary parts, that is I is common and v dx plus u dy, that is real part and that is imaginary.
Now here we will take the help of Green's theorem.
Green's theorem, that is integration of m dx plus n dy is equals to double integration of del n upon del x minus del m upon del y into dx dy.
Now we will apply the Green's theorem on the above equation. That is integration of f of z dz is equals to double integration of minus del v by del x minus del u by del y. Take second term first and first term second into dx dy. Here I'll also use the same process, that is integration of c del u by del x minus del v by del y. Take second term first and first term second into dx dy.
Later on, replacing the value of minus del v by del x by del u by del y and del v by del y by del u by del x. Replace both the values on that equation. Double integration of r del u by del y minus del u by del y dx into dy plus I double integration of c del u by del x minus del u by del y dx into d. Both the terms are same, that is 0 plus I into 0, that is integration of f of z dz is equals to 0.
And this is the target of this theorem. Integration of f of z dz is equals to 0. Hence proved the Cauchy integral theorem. For more understanding, we will take the example based on this theorem, and this example is explained by my friend Swati in upcoming part. Thank you.
Hello everyone, my name is Swati Humne and today I am going to explain a problem using Cauchy's integral theorem. I will only give you a brief overview of this topic because my friend Kalyani has already explained it in previous part. So, this fundamental theorem is complex analysis state that if a function is analytic inside and on a simple closed contour then the counter integral of that function is 0. Using this powerful result, we can simplify complex integrals efficiently. I will now walk you through the step-by-step solution of the given problem. Let's begin. So this is the question we are going to deal with, which is integral of function over c z square plus a divided by 0.5 z minus 1.5 dz x square plus y square is equals to 16. So the given integral is I is equals to integral of function over c z square plus a divided by 0.5 z minus 1.5 dz, where c is the circle. X square plus y square is equals to 16. So we can write mod z is equals to 4. Now we will solve this using Cauchy's residue theorem. We first identified the singularities of the function inside the given contour. So the denominator is 0.5 minus 1.5 is equals to minus 1. Now we will solve for z. That is z is equals to 1.5 divided by 0.5 is equals to 3.0. So the function has singularities at z is equals to 3, since the counter is mod z is equals to 4 and 4 is greater than mod 3. These singularities lies inside the contour. Now we write the function that is fz is equals to z square plus 8 divided by 0.5 minus 1.5 dz. Now to find the residue at z is equals to 3, we again rewrite the function as fz is equals to z square plus 8 divided by 0.5 into the bracket z minus 3. Now again we rewrite the function as fz is equals to z square plus 8 divided by 0.5 into 1.z minus 3. So this will be now to find the residue at z is equals to 3, we evaluate the coefficient of 1 by z minus 3, which is residue f dash 3 is equals to 2 in bracket 3 square plus 8, that is 2 into 9 plus 8, and further we simplify, so the answer is 34. Now the last step, that is we apply the residue theorem, which is I is equals to 2 pi I into residue F3. Now we will substitute the residue that is I is equals to 2 pi I into 34, that is 68 pi I. This is the final answer of our question. Thank you.